Hello everyone, welcome to SS Talks Chemistry. I hope you all are doing great. So we were discussing the previous year questions of the CSIR NET exam, and in that the unit that we started, it was your molecular spectroscopy, or we can call it as our physical spectra. Already one of the part of this unit we have discussed. Now this video is gonna be the part number 2, where the remaining questions we will be discussing. Okay, so in the first part till the June 2019, that was from June 2011 to the year to June 2019, we have discussed the questions. Now from December 2019 to the last 2025, we are gonna discuss these questions. Okay, if you want to have a look to the previous one, the playlist I have made on the channel, or the link will be provided in the description. Even from that you can get the access to that. Okay, and before starting the video, if you are coming to the channel for the first time, make sure you subscribe to the channel also, so that you can get notification for the upcoming videos too. Okay, so now let's start with the questions. The very first question, as I said, it's from the CSIR NET exam conducted in December 2019. The question, it says the frequency of the OH stretch occurs at 3600 centimeter inverse. The OD stretching frequency in centimeter inverse, it would be closest to. So what they have given, the stretching frequency for the OH bond, it is given. It is 3600 centimeter inverse, and the stretching frequency for the OD bond is being asked to us. So isotopic leveling concept is being done over here. So now I know that stretching frequency general formula you have, it is 1 by 2 pi c into the root of k by the mu. Okay, so we can say that stretching frequency, it is inversely proportional to the under root of the reduced mass of it. So now we can compare it for the given one, that is of the OH with the OD. Now stretching frequency of the OD bond to that of stretching frequency of the OH, it will be equal to under root of reduced mass, that is of the OH, upon the reduced mass of the OD. Right? Now what is the reduced mass? We know the 1 by mu, it is 1 by m1 plus the 1 by m2 of it, or we can say it is m2, or the m1 plus m2 upon the m1 into the m2. This is 1 by mu value you have. So the reduced mass value, it is m1 into the m2 upon the m1 plus of the m2 of it. So this formula you have for the reduced mass that we are gonna use now. Okay, so instead of m1 and m2, the masses of oxygen and hydrogen will be taken in one case, and in the other case masses of the oxygen and deuterium. So it will be equal to under root of, now mass of oxygen, it is 16 into the 1 upon the 16 plus of the 1, right, upon the reduced mass of the OD, that is 16 into the 2 upon the 16 plus of the 2. This it will be there, right? So we can say that, let's just shift on the new one, new slide, let's just shift. Okay, so it's becoming the reduced mass of 16 upon the 17, and here it was 60 as 18 it was there, because 16 plus 2 we are doing, so that goes in the numerator, and here it will be 16 into the 2 of it. So here 16 and 16 it gets cancelled, and 2 and this 9 it becomes. So under root of 9 by 17, this ratio we are having, that is for stretching frequency of the OD to that of the stretching frequency of the OH. So stretching frequency of OD, it will be under root of 9 by 17 into the 3600 centimeter inverse, which was stretching frequency of the OH. Right, on solving this, the value we will be getting, which is gonna be 2619.3 centimeter inverse of it. This is the value you are getting. So now from the options, if I see, the closest one is being asked, so around 2600 the value will be there. So option B becomes the right one. Okay, now let's move to the next question. This one again from the same paper only. It's saying that in the pure rotational microwave spectrum, the pure rotational microwave spectrum of a XY molecule, the adjacent line. So what is the gap between the adjacent lines? It is of the 2b, right? Like this, the gap you have it. Because the ground state here, it is the not the most populated state you have it. So J max value at some other than the ground state, the value we obtain. So something like this the plot you get, right? Now here the adjacent lines, the gap it is of the 2B gap, right? So it goes like this. So 2B gap, this value it is given, 2B value it is 4 centimeter inverse of it. If the molecule it is irradiated by the radiation of 30,000 centimeter inverse, the first Stokes line it appears at. So here now about the Stokes and anti-Stokes lines. So here is the central, which is the Rayleigh line that you can see, which is of the incident. At a certain gap, here you get the Stokes lines. On this side you get the Stokes lines, and on the right side we get the anti-Stokes lines. These are the anti-Stokes and these are your Stokes lines. Now the gap that you have in this, the first line, the gap here it is of the 6B. Here also it is of the 6B. Then the adjacent gap you have, which is of the 4B gap, like this. On both the sides it gaps, it continues like this. Okay, so now we are asked for the first Stokes line. So first Stokes means this line, the value is being asked. This value they have given us to be 30,000 centimeter inverse of it, right? So from the pure rotational spectrum, the B value we found it that it is 4 by the 2, which is equal to the 2 centimeter inverse of it. So using the pure rotation, you are finding the B value. Now the Stokes lines. Stokes line, it is gonna be the new that is used for the incident minus of the 6B of it. Had it been the anti-Stokes, then this value you will be adding in that. Okay, so it becomes 30,000 minus of the 6 times the 2, that means 30,000 minus of the 12, it will be there, right? So on solving this we get the 29988 centimeter inverse of it. So this is the line where the first Stokes shift you are gonna observe. So option A, it becomes the right one. Okay, moving to the next. This question now, it's from the CSIR exam conducted in the 2020. The question it says the vibrational transition energies of a diatomic molecule corresponding to from the new value which is 0 to new value 1 and the new value 1 to new value 2. So here the vibrational levels you have like this. The here is nu is equal to 0, this is 1, this is 2, and like this the higher levels you are also having. So first transition is from 0 to 1, this is called as the fundamental band. It is the fundamental band you have. Its value it is omega e minus of the 2 omega e into the xe of it. This is what we get, right? Now the next transition it is from the 1 to 2. So here it is 1 to 2. These when the excitation to the higher energy levels it is taking place from the excited states only. These are called as the hot bands. These are called as their hot bands. Okay, had it been the transition it is taking place from 0 to the not the 1, it is going directly to the 2. These are called as the overtones. 0 to 1, 0 to 2, 0 to 3, 0 to 2 it is first overtone, then the 0 to 3 it will be second overtone, like this it goes on. So these are the different types of the bands that you obtain in the vibrational spectra. Okay, so now the value of your this fundamental band it is given, the value is 2143.1. so omega e minus of the 2 omega e into the xe, this value we have 2143.1 centimeter inverse of it, right? Now let's find the value of the hot band also. So for the hot band, the energy difference, firstly you see the general formula for the nth state, the energy value you have, it is n plus of the half into the omega e minus of the n plus of the half into the its square, you take it into the omega e into the xe of it. Now we are going from the 1 to 2. So energy gap, it will be energy of the second state minus the energy of the first one. So n value you keep it as 2. So 2 plus of the half, that becomes 5 by 2 5 by 2 omega E minus of 25 by 4 omega E into the XE minus of. Now for the first one, it will be 3 by 2 into the omega E minus of the 9 by 4 into the omega E into the XE of it, right? So it is becoming 5 by 2 minus 3 by 2, that will be omega E minus of. Now 25 minus of the 9, that is 16. So minus of the 16 divided by the 4, that is 4 omega E into the XE of it. So this value is of the hot band, first hot band that you are obtaining, and this value is given, which is 2116.1 centimeter inverse of it. Okay. So now I am having the value of the omega E minus of the 2 omega E into the XE, which was 2143.1 centimeter inverse, and the other value, which is omega E minus of the 4 omega E into the XE, it is 2116.1 centimeter inverse of it. Now I just need to find the value of this only, which is n-harmonicity constant omega E into the XE of it. So for that, what you do is you just subtract both of this. So these two gets cancelled. 2 omega E into the XE, this will be equal to 27, right? So from here, omega E into the XE, it is 27 by the 2, that is 13.5 centimeter inverse of it. Okay. So now from the options we can see 13.5, the option B will be the right one. I hope it's clear. Okay. So now let's move to our next question. This one, again the NET 2020 exam only. The energy separation for the carbon, which is having the 12 isotope, and oxygen 16 isotope, the rotational energy levels between J double dash value as 3 and the J double dash value as 9, it is 24 centimeter inverse. The rotational constant is closest to for 13 isotope of the carbon. Okay, so here firstly we need to find this energy gap. So here, then for the jth level, the energy value you have, it is Bj into the J plus of the 1, right? Now the energy difference is for the E9 minus of the E, that is of the third state. So it will be B into the 9 plus of 1 minus of the B, which is 3 into the 3 plus 1. 3 into the 3 plus of the 1. So it becomes 90B minus of 12B. So this gap, it is 78B. This value it is given, it is 24 centimeter inverse. So this rotational constant, if you find it out from here, it is 24 by the 78 centimeter inverse. But this rotational constant we are having, it is for the carbon 12 and the oxygen 16, because their data it was given to us. Now I know that B value, it is h upon the 8 pi square into the IC of it, right, in centimeter inverse. If the rotational constant value is there, so this is the formula that you use, right? So here we can see that I value also we know it is equal to the mu r square. So B value, it will be h upon the 8 pi square into the mu r square into the C of it. So I am seeing that B value, it is inversely proportional to the reduced mass, right? So this concept now you can use so that the rotational constant for the carbon 13 isotope we can find it out. So rotational constant for the carbon 13 and the oxygen 16 upon the rotational constant, which is for the carbon 12 and oxygen 16, it will be equal to reduced mass of the 12 isotope of the carbon upon the reduced mass, which is of the 13 isotope of the carbon, right? So now the values which are given, just substitute that. This value we need to find it out. This we have found it as 24 upon the 78 centimeter inverse. This is equal to, now 12 into the 16 upon the 12 plus of 16, which is the reduced mass of the 12 isotope of the carbon, and upon that of 13 into the 16 upon 13 plus of the 16, right? So it's becoming 12 into the 60 upon 28 into, here the 29 that will be going in the numerator upon the 13 into the 16. So here the 16 and 16 it will get cancelled out, right? And that rotational constant also you can shift it 24 by 78. So this will give you the rotational constant for the carbon 13 isotope, right? Just solve this and find your value. We will be getting the answer, that is your 0.294 centimeter inverse of it. This is gonna be the value. So this is only gonna be the answer that we will be getting, but from the options if I see, none of the options it is matching. So there might be some correction in the options, might be some error is there. So the value it is 0.294. So here you can change this one. It's 0.294. So we can say A will become the right one. Okay. Methodology you have to follow is this one only, right? Next, this question now, it's from the June exam of the year 2021. The question it says the correct statements for the following sets 1 to 4 is. Okay. The first statement it states the Q is the displacement from the equilibrium for the harmonic motion. The potential energy is proportional to the Q. Okay. So we have harmonic motion, which means they are talking about the simple harmonic motion, that is your SHO, right? Now in the simple harmonic motion we see that force value, we say it is proportional to the displacement in it, right? So this is according to the Hooke's law. Hooke's law you have it, right? Removing this proportionality constant, force it is coming out to be kx. Now the displacement is in the opposite direction, so negative sign is placed in front of it. Also we know that force value it is minus of the dv by the dx of it, right? So equate both of this, minus of the kx it is gonna be minus of the dv by the dx of it, or we can say dv value it is k times the x into the dx of it. Now integrate on both the sides, it will become potential is equal to half of the k x square of it. So this is the potential value that you obtain. So here instead of the x, the displacement they have used is q symbol now. So x is my q only. So here the potential will be half of the k q square only, right? So potential we are seeing it is proportional to the q square, but here they are saying that potential energy is proportional to q. So this statement is the incorrect one. So from this statement only, if you see, we have to choose the correct one. The first option, if you see, it is saying that first statement is the true one, incorrect. Second, again it is saying the first is the correct, again the incorrect. Third, we are just leaving because one is not included. Fourth option also, you see, one is saying they are saying it to be the true one, so again it will be the incorrect one. So from the first statement only we can interpret the correct answer is gonna be the option third one. But let's check the remaining statements also. If the vibrational frequency of the HCl it is 2990 centimeter inverse, the 0 point energy will be 14.95 centimeter inverse. So what is basically the 0 point energy? It is called as the ground state energy. This is the ground state energy. Now in the vibrational levels, the particles they are never at rest. They have the certain energy in them. So the general formula for the energy you have, it is n plus of the half into the h nu of it. This is for the simple harmonic motion. Now the n value it is 0 for the ground state. So it will be half of the h nu. Right. Now this h nu value it is given to us, which is 2990. So just divide this with the 2, the value we get 1495 centimeter inverse only. So this statement which is saying that the value of 0 point energy is 14.1495 centimeter inverse, this statement is the correct one. Okay. Next, the correct order of the vibrational frequency for the oxygen and the protium. Oxygen and the deuterium it is x2, and oxygen and the tritium it is x3. Their vibrational frequency order is being asked to us. Okay, so let's do. We know that stretching frequency, it is 1 by 2 pi c into under root of k by mu of it. So nu value, it is inversely proportional to the under root of the masses. Now various bonds that you have: protium, oxygen and the protium, oxygen and the deuterium, oxygen and the tritium we are having, right? So here the maximum reduced mass, we can see it is for gonna be for the OH with the tritium, then it is gonna be OH with the deuterium, and it is gonna be then least for the oxygen and the protium, right? So it is inversely proportional, so frequency order will be the reverse of it. That means tritium one will be having the least, followed by the deuterium one, and maximum one will be for the protium one. This they have said it that this is x1, this is x2, and this is the x3. So we can say that x1 is greater than the x2, and then the x3 value you are gonna have. So this is the order that we are observing in it. So let's see from the statement. The correct order of the vibrational frequency of this x1 is greater than x2 is greater than the x3. This is what we got only. So that means this statement is also the correct one. Okay. Next, the fundamental vibration transition of a diatomic molecule, it appears at 1880 centimeter inverse. So first is the fundamental vibration, that means from V value 0 to V value which is 1, that means omega E minus of the 2 omega E into xe. This value it is given 1880 centimeter inverse of it. It appears at this. The first overtone, it will be appearing at 940. This is what they are saying, assuming the n harmonicity constant as 0, that means xe value they are saying we have to assume it to be the 0 1. So let's do this. Here only we can solve it. So here firstly it is omega E minus of the 2 omega E into the xe, which is 1880 centimeter inverse they are saying. If I consider the xe value as 0, that means omega E will be 1880 centimeter inverse of it. Now the overtone value, first overtone will be at 2 omega E minus of the 6 omega E into the xe of it. Again we can consider the xe value as 0 only. So first overtone, it will be at 2 omega E. That is 2 into the 1880 centimeter inverse. At this value it should come, which is 0, 16, 17 and 3760 centimeter inverse. At this the value you should obtain, but the given value it is at 940 centimeter inverse only. So that makes this given statement to be the incorrect one. So only the second and the third are correct. That too we got it. So option third is the right answer. Okay. Now the next question we are having, this one, it's again from the June 2021. Table has been given where the measurements have been given and the spectroscopic techniques have been given. We have to just match them, that which of the following spectroscopic technique is used for the measurement of the which of the following things. Okay, so first it is about the binding energy. So binding energy we can find it using the X-ray. Binding energy, binding energy, this we find it using the X-ray spectroscopy. X-ray spectroscopy. So as you can see, the option A, it is matching with the third one. A will be matching with the third one. Okay. So A is with the third one. Next, it is about the quadrupole splitting. The quadrupole splitting, we measure it using the Mossberg. That means with the B, the fourth one we will be having. Now with the C, which is the contact shift, which means about the chemical shift values they are asking. So this value you can find it using the NMR technique. Right, so C will be matching with the first one, and D we are left, that is gonna be elemental analysis, that is done using the energy dispersive X-ray spectroscopy. So D will be matching with the second one. Okay, so 3, 4, 1 and 2. So let's see, A with the third, B with the fourth, C with the 1 and D with the second. Option first one only is the right answer, I guess. right? A with the third, B with the fourth, C with the first, and D with the second one. So first is the right one only. Okay. Now moving to our next question. This one again from the June 2021. The molecule that will not observe in the microwave region but will observe in the infrared region. So what are the conditions for a molecule to be microwave active and for the IR active? For the microwave, molecule should possess the permanent dipole moment. Permanent dipole moment the molecule should possess. Whereas a molecule to be IR active, there should be change in the dipole moment. Change in the dipole moment, it should be there. Right. Now from the given molecules, firstly it is the N2 molecule you are having. So N, triple bond N only. So mu value here it is 0. That means it is microwave inactive. Microwave inactive. And also we can say that there is not gonna be any change in the dipole moment also. So it is gonna be IR inactive also. Right. So first we have to choose the one which is microwave inactive but is IR active. That is the molecule that we need. Next, it is C2H2. So this type of the molecule you have, it is the hydrogen, 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 and this hydrogen. So here in this case also you see the dipole moment it is 0 only. That means it is microwave inactive. Microwave inactive. But here you can see the various types of stretchings are possible in it, right? We can have the symmetric stretch or the asymmetric stretch, or we can have the bending in it, right? So if I do the bending modes, you can consider like this. If you bend it, the change in the dipole moment is not 0. Change in the mu is not 0, suppose in the bending mode, so it is IR active, right? So answer is gonna be the option B only, but let's check the remaining ones also. See, it is saying that it is your HCl. So HCl, electronegativity difference, this is delta negative, delta positive. Mu value is not equal to 0, which means it is your microwave active. Microwave active. I needed the molecule should be microwave inactive. So this can't be there. And the D1, it is the water. So D, which is the water. So again you can see here the hydrogen and this oxygen is present. This is delta positive, this is delta negative, here also it is delta positive. So the dipole moment it is not equal to 0, so it is also the microwave active, right? So C and D options can't be there, so option B only is the right one. Okay, next this question. The following data is obtained for the light diatomic AB molecule, okay, from its rotational Raman spectrum. So what type of spectra is given? It is rotational Raman spectrum has been used, where the B value is 2 centimeter inverse, XE value is this much, nu E value it is 1600 centimeter inverse. If the molecule it is radiated by the 20,000 centimeter inverse, the expected Stokes lines in centimeter inverse of for this molecule it is. So if I consider the pure spectra only, so there is gonna be this Rayleigh line and corresponding Stokes line. This is gonna be at a distance of the 6b from here, right? So here if I see the radiation, it is at 20,000 centimeter inverse at the 6b. So that 6b if you subtract from this 20,000 minus of the 6 times the 2. So 12 you have to subtract from here. So you will be getting the value at 19988 centimeter inverse. At this the value you should obtain. But in none of the options you see the direct values, they are not given. That means only the rotational levels. If I am considering that the gap is of 6b, this is not giving me the answer for it, right? So here what I have to take is various levels I have to consider. So we know that these various vibrational levels you have. Now in between the various vibrational levels, various rotational energy levels, they are also present in it, right? So here V value we can consider it as 0. This is the one. This is J value 0, J value 1, J value 2, like this. The various transitions, they are also these levels, they are also present. So if the molecule is going from V is equal to 0 to V is equal to 1, where the more these rotational levels will be present, so various types of transitions are possible. So that means along with the rotational energy levels change, vibrational energy level, it is also changing, right? So that means from the incident radiation, the sum of the energy which you are requiring for the vibrational transition as well as for the rotational transitions, that has to be taken into the consideration. Okay, so that means here the energy values you will be taking. Now let's consider first the various vibrational levels that we are having. So the energy corresponding to the firstly vibrational levels we will be seeing, and then for the rotational energy levels we will be moving upon. So for the vibrational energy levels, the energy for the vibrational energy levels, this we have n plus of the half into the omega e minus of the n plus of the half, the square of it into the omega e into the xe of it. This is the value that we have. Now for the ground state, that is E is equal to 0, the energy it will be half of the omega e minus of the 1 by 4 omega e into the xe of it. This is the value that we will be having. Now here this value of the nu e, it is already given to us. That xe value you are having it as 0.01 and nu e value is 1600. So that you can substitute. So it will become half into the 1600 minus of the 1 by 4 into the 1600 into the 0.01, right? So this value it comes out to be as 800 minus of, this is 400, so 800 minus of the 4, that is 796 centimeter inverse. So this is for the ground vibrational energy level. Now for the first state of the vibration, the energy will be 3 by 2 into the omega e minus of the 9 by 4 into the omega e into the xe of it. So it will become 3 by 2 into the 1600 minus of the 9 by 4 into the 1600 into the 0.01 of it. So this value we get 2400 minus of, now here these zeros are getting being cancelled, 9 fours are, it becomes 36. So 2400 minus 36, that becomes 2364 centimeter inverse. That means the change in the vibrational energy that you get, it is equal to 2364 minus of 796 centimeter inverse. So this value we get, which is 1568 centimeter inverse of it. So for the vibration, since the ground state is the most populated one, so you take the intense band only. So fundamental band is taken as the energy change only, right? Now for the various rotational levels, how is the energy changing? Let's see that. For the rotational energy levels, the energy you have, it is Bj into J plus of the 1 of it. Now we are looking upon to the Stokes line. For the Stokes lines, the selection rule is delta J value, it should be plus minus of the 2. That means delta E gap that you obtain, it is Bj plus of the 2 into the J plus of the 2 plus of the 1 minus of the Bj into the J plus of the 1. Right, this is the gap in the J value and the J plus of the 2th level. So it will become Bj plus 2 into the J plus of the 3 minus of the Bj into the J plus of the 1, right? So we can further expand this also. J plus, it is 3 over here. Here it is J plus 1. So we can expand this also. On solving all of this, you get the value B into the 4J plus of the 6 as the delta E value. Right. Now various types of transitions are possible. So if you consider transition is from J value, that is 0 to 2 if you consider. So delta E value, in that case it will be B into the 4. From the 0th level it is taking place, so that level from which the transition is occurring, that J value you have to take it, so it will become 6B, right? Similarly, from the first level also it is possible, that will be to the third one. In that case, delta E value, it will be B into the 4 into the 1 plus of the 6, that becomes the 10B of it, right? Similarly, from the second level also it is possible, from the second to the fourth it will be going, so delta E value, it will be B into the 4 into the 2 plus of the 6, right? So 8 plus of the 6, that is 14. 14 B the gap you will be having. Similarly, from 3 to 5 level it will be going, so in that case B 4 into the 3 plus of the 6, so 12 plus of the 6, that is 18 B you will be getting, right? Now next, from the J value, that is 4 to 6, it is also possible. So in that case, delta E value, it will be B times 4 into the 6 plus of the 6. So that means 24 plus of the 6 it is becoming, that is 30B the value you are getting. Sorry, here it will be 4 over here, not the 6. So 4 4s are, it is 16 plus of the 6 we have to do. So 16 plus of the 6, that becomes 22p, right? Now the B value, it is given to us in the question only. B value, it is 2 centimeter inverse. So delta E gap, it will be now 6p, it will become 12 centimeter. This will become 20 centimeter inverse. Now next, it will be 28 centimeter inverse. This will be 36 centimeter inverse, and this one, it will be 44 centimeter inverse. Now we have got the various rotational levels and the vibrational energy level gap also we have obtained. So the nu, that is for the Stokes line, this is gonna be the nu which is for the incident minus of the delta nu which is the total one. So total one, it means delta nu which you have for the vibrational plus the delta nu that you are having for the rotational energy levels, right? So this sum, if you subtract from the incident, now you will be getting the stretching frequencies for your stock lines. So the incident one, it was at 20,000, right, minus of. Now the gap for the vibrational, that is from 0 to 1 level, it is 1568 plus of. Now for the rotational, various rotational energy levels change, it is taking place. So first it is at 12 centimeter, so to subtract that, so it will be 12 centimeter. On solving this, the value you obtain, that is at 18420 centimeter inverse of it. Similarly, the next rotational level, so if it is from J is 0 to 2 the level you are taking, right? J value, if it is from 1 to 3, so in that case the stock shift, it is gonna be 20,000 minus of 1568 plus of the, here the next level, the energy, it is 20 centimeter. So this 20 you will be subtracting. So the value you obtain at 18412 centimeter inverse of it. Similarly, for the J value, which is 2 to 4, so in that case it will be 20,000 minus of 1568 plus of the energy you got it 28. So plus of the 28 from this. So 8 you need to subtract from this. It will become 404 centimeter inverse of it. Right. Next, from the J value, that is 3 to 5. In that case, it is gonna be 20,000 minus of the 1568 plus of the, here the value you obtained, that is 36. So this will give me the value 18396 centimeter inverse of it. Similarly, for J value 4 to 6 also we can find it. So it will be 20,000 minus of the 1568 plus of the, there the value you obtained 44. So this was 44. So this will give me the value 18388 centimeter inverse of it. Similarly, from the fifth level also you can see, if you take, you can see here the gap that you obtain from J value 5 to the 7, 4 times the 5 plus of the 6. So that means it is gonna be 20 plus of the 6, which is 26b. That means it is gonna be 52 centimeter inverse of it. So delta nu for the stock shift, in that case it is gonna be 20,000 minus of the 1568 plus of the 52. So that comes out to be at 18380 centimeter inverse. So now you can see the various stock lines that I am getting, it is in the range of 1800. Now let's match these values. So first is 18420. 18420, the values you see, 18420 in this I am having, and 18420 in this also I am having. Right. Next stock line, it is at 18412. 18412 again in this, and again in this also I am getting. Next it is at 18404. So 18400, close to that only. So 18400, this value you are having, right? The next one, if you see, 18396. 18396, that value is not given, no worries. Next it is at 18388. 18388. So you can see in this the value we are having. In the above one, 18388, the value we are not having, right? Next value you see, it is 18380. So 18380, again you see in the option C it is given. So that means all the stock shifts lines that have been given in the option C, they are matching, right? That means not only the respective rotational levels gap you were considering, firstly the vibrational energy gap it was taken, and along with that the rotational gaps we were to take into the consideration to find the overall stock shifts. Okay, so this is how this question it was to be solved. Okay, I hope it's clear. Now let's move to the next question. This one we are having, it's from the NET exam conducted in the June month of the year 2022. A schematic potential energy surfaces for the bond, which is bending motions, are indicated as the A and the B in the accompanying diagram. The out of the plane CH wedges in the iodoform and the chloroform would be respectively corresponding to the potential energy surfaces. Okay, so two of the molecules have been given, which is iodoform and the chloroform. From that, this diagrams has been given, which is for the potential energy surfaces, right? So I know that what is the basic formula for the iodoform. You have the carbon and the hydrogen, and here these three iodines they are present, and in this you have the carbon and the hydrogen, and three chlorine atoms they are present, right? So what difference is there between the two of the molecules? Basically that is of the bond length of the carbon and chlorine and the carbon and the iodine bond. So here you see the bond length of the carbon iodine bond, it is very large as compared to the carbon chlorine bond in it, right? So that means in the carbon chlorine bond the bond length is not very large. So this carbon and the Cl bonds, they will be present close to the one another, right? So they will be present close to the one another. So there is gonna be lot of the repulsion present between them, right? So repulsion is present, that means more they will be trying to move far apart from the one another, which means more bending it will be observed in their case. Whereas in the carbon iodine, the bond is actually like this. You can see they are moving very far apart, like this. They are very far apart. There is not much repulsion in them. Bond length it is large, so there is less repulsion between them. So there is gonna be less bending in them. Okay, so that means from this one potential energy that has been given, the central line, the one which is showing the less bending, which is the A1 that you are seeing, this displacement is basically representing the bending that you are observing. right? More repulsion, that means more displacement from the main position. Here the less displacement, that means it is corresponding to iodoform, and here is the more displacement, that is due to the more repulsion, so this is corresponding to the chloroform, right? So firstly is the iodoform is in the A and chloroform is in the B1. So A and B, option A, it becomes the right answer. Okay. Now next, this question. Consider the following statements about the infrared spectroscopy. Okay, first it says it is used to determine the band gap, the band structure and change, and the charge carrier concentration of the compounds. So no, concentration of the compounds I can find it using the UV visible spectroscopy, not the IR one, right? Next option, it says it is used to identify the functional groups of the compounds. This statement is the correct one. The stretching frequencies of the various bonds showing the change in the dipole moment are determined in the IR spectroscopy. So B is the right answer, right? Next, it is used to characterize the different stretching and the bending vibrations in the molecules. Rest options are not the ones. The most opt one answer, that is the B1 in this. Okay. Now next, this question. The rotational absorption spectrum for the HCl, which is of the isotop 35, is shows the following lines. Okay, for the J going from 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, the values of their stretching frequencies they have been given to us. Now, neglecting the centrifugal distortion, the value of the rotational constant in the units of centimeter inverse of it. So here the rotational spectra has been given to us. In the rotational spectra, the adjacent lines gap is of the 2b 2b, right? So this is the 2b 2b gap that you have. So any of the values we can take. So I am assuming from 5 to 6 and 4 to 5 values. So the gap is 1 to 4, 124.30 minus of the 104.10. So the difference we are getting, which is 20 and 0.2020 centimeter inverse. This gap it is corresponding to 2b, right? So B value it is 20.20 divided by the 2, that becomes 10.10 centimeter inverse of it, right? So close to 10, option third will be the right answer. Okay. Next, this question. Now, again the June 2022, the vibrational energy for the nth state of the HCl is approximately given as this. The vibrational quantum number n max it beyond with the beyond which HCl undergoes dissociation at. Okay, so basically what happens in the n harmonic oscillators, you obtain this type of the spectra. Like this, you obtain the curve, not the spectra, sorry. It is the potential energy curve that you obtain. For the simple harmonic motion, it was like this. Like this you obtain. That is, the bond breaking in that case, it is not shown. But in H1, the bond it breaks at a certain point beyond this level. Now here the various levels you are having. The largest n value of the n beyond which your bond is breaking, that is the value which is n max. This value it is n max. Beyond this level if we are going, the bond is gonna break. Okay, so this is what we have been calculating also, the dissociation energy values, right? This complete level, this is called as the dissociation energy. Some energy is possessed already, that is called as the 0 point energy, and this value, the difference between them, it is the true dissociation energy, that is d naught, the additional energy that you are providing for the bond to dissociate. Okay, so now this value of the n max is being asked to us. So how do we find the value of the n max? That is the energy value you have, it is n plus of the half into the omega e minus of the n plus of the half the square into the omega e into the xe. So what you do is you differentiate this energy with the n and equated this to the 0. From this, the value of the n that you obtain, it is called as the n maxima. Okay, the value that you obtain, it is half of the xe, half of the xe is also in the denominator, minus of the 1 by 2. This is the value for the n max after this differentiation that you obtain. So if you remember the direct formula, it's okay, but at some point if you forget, you should remember that what basically is the meaning of this n max value. So the maximum value of the n beyond which the bond is gonna dissociate. How can I find it? By differentiating the energy values with the n values, right? So here this energy in terms of the Gn they have given, so just you can differentiate with this with the n value and you can get your n max value. So let's do this. So G of the n, it is given to us 3000 into the n plus of the half and minus of the 50 into the n plus of the half, the square of it. Two of the methods I'll be telling. First one is through the differentiation I'm doing. So dg by the d of the n equated to the 0. So dg by the dn, it will be 3,000 into, now differentiating it with respect to n, so n with respect to 1 it will be 1 only, half is a constant so that will become 0, minus of 50 into the 2 times n plus of the half into the 1 only, this is equal to the 0. So from here I get 3000, this is equal to 50 into the 2 into the n plus of the half of it. This n that you will be getting, it will be your n max only. So here you see this 0 and 5 2s are is 10, so this 2 will be eliminated. So 30 minus of the half, this is gonna be the n max, that is 29.5, it is gonna be the n max, right? So this is the first method. So answer we are getting it as 29. So option first one will be the right one. So this after differentiation you get. The second one, what you can do is just do the comparison of it. This is the second method. The given energy you have, it is 3000 into the n plus of the half minus of the 50 into the n plus of the half, the square of it. Now the general formula for the energy you know, it is n plus of the half into the omega e minus of the 50 into the fifth, instead of the 50 it is omega n plus of the half, the square of it into the omega e into the xe. From here you can see the omega e value you are getting it as 3000 and omega e into the xe is 50, right? From here the xe value we can find it out, omega e into the xe upon the omega e, which is 50 upon the 3000, right? So 5 6 1 by 60 the value you are getting. Now the value of the n max we know it is half of the xe minus of the half, so it will be 1 by 2. Xe value is 1 by 60, so 60 goes in numerator minus of the half, so again it becomes 30 minus of the half only, that we are getting it as 29.5 centimeter inverse. So this formula you can use if direct formula for the n max you are knowing. If you are not knowing, then go with this first method, which is the differentiation. So same answer you are gonna get. Okay, I hope it's clear. Now moving to the next one. This question you have, it's from the CSIR NET exam conducted in the December month. The combined paper it was there, which was for the December 2022 and June 2023. The question it says the vibrational energy for a diatomic molecule is given by. Again the energy expression is given where nu e is the fundamental frequency and xc is the n-harmonicity constant. The IR infrared spectrum for the BeO molecules in the excited state shows two of the transitions at 1078.48 centimeter inverse and the other values given, identified as the transition between the levels. Now these levels are 2 to 3 the transition is occurring, that is giving me this value, and 3 to 4 this value you are having. Okay, so the value of the nu e and the nu e into the xe for the BeO molecule we just have to tell them. Okay, so the general formula for the energy it is already given to us. It is n plus of the half into the nu e minus of the n plus of the half, the square of it into the nu e into the xe of it, right? So firstly the transition which is from 2 to 3. So that means the energy for the third level minus the energy for the second level. So for the E3 level, the energy it is gonna be 3 plus of the half it will become 3 plus of the half into the nu e minus of the 3 plus of the half, the square of it, nu e into the xe minus of. Now for the second level, 2 plus of the half into the nu e minus of 2 plus of the half, the square of it, nu e into the xe, right? So this is becoming 7 by 2 nu e minus 49 by 4 nu e into the xe minus of the 5 by 2 into the nu e plus of the 25 by 4 nu e into the xe, right? So 7 by 2 minus 5 by 2 nu e, that will become nu e minus of 49 plus of 25, so minus of 16 by 4, that is 16 only. It is, I guess it is, we are getting, so let's just check. So it is 4, sorry, so it's 24 upon the 4, that is 6. So 6 nu e into the xe. So it's becoming nu e minus of the 6 nu e into the xe. This value is 1078.48 centimeter inverse of it, right? So first equation we have got nu e minus of the 6 nu e into the xe is 1078.48 centimeter inverse of it, right? Now for the next, which is for 3 to 4 level, for the 3 to 4 level, energy of the fourth level minus the energy for the n value, which is 3. So 4 plus of the half into the nu e minus of the 4 plus of the half, the square of it, nu e into the xe minus of 3 plus of the half into the nu e minus of 3 plus of the half, the square of it into the nu e into the xe of it, right? So this is becoming 9 by 2 nu e minus of 81 by 4 nu e into the xe minus of, now 7 by 2 nu e plus of the 49 by 4 nu e into the xe. So 9 by 2 minus 7 by 2, again nu e we will be getting. Here it is minus of 81 plus of the 49 upon the 4 into the nu e into the xe. So this is coming out to be 11 minus 9, that is 2, and 7 minus 3, 7 minus 4, that is 3. So this into the nu e into the xe, nu e minus of 32 by 4, that is becoming nu e minus of the 8 nu e into the xe. This value it is given to us as 1062.42. 1062.42 centimeter inverse. So this is the second equation that we have framed. Now using these two equations, we can find easily the value of the nu e and the nu e into the xe. First, nu e minus of the 6 nu e into the xe, 1078.48 centimeter inverse, the value we got, and nu e minus of the 8 nu e into the xe, 1066. Yes, only it was there, no? 1062.42. 1062.42 centimeter inverse. So just subtract both of this. These two will get cancelled. 2 times the nu e into the xe we are getting. This is 606. 16.06. So nu e into the xe we are getting it as 8.03 centimeter inverse. So this value of nu e into the xe we have got. Now from the options, if you see nu e into the xe 8.03 in this option I can see, and in this, from this value second and third it will be eliminated. Now nu e value, by substituting nu e into the xe in any of the above equations we can find it. Nu e minus of the 6 times the 8.03, it is 1078.48. Now this has to be added. Nu e will be 1078.48 plus of the, now 6 3s are, it is 18 point, now 6 8s are, it is 48. So add both of this, we will be getting, so 6 and 4 and 5, 6.6 over here. So again 16 it is becoming, 7 plus 4 is 11 plus 1, it is 12. So 1126.66 centimeter inverse. This is the nu e value you are getting. Now from the options, 1126.66, The option first will be the right one. Here some different value was given, so again fourth will be eliminated. Okay, so this is how this question it was to be solved. I hope it's clear. Now moving to the next one. This question you are having. So it's from the December 2023 now. Consider the nuclear shapes of the nitrogen, which is 7 isotope, and oxygen, which is 8 and 17 isotope has been taken for it. We have to tell them about the prolate and the oblate molecules. So these are the symmetric top molecules they are talking about. From the nuclear spin values, you can also tell if the nuclear spin value, which is I value, it is 0 or it is the half value. These type of molecules, they are prolate. Okay, and if the nuclear spin values, they are greater than equal to the 1, that means 1 2 3 like this, the values you are getting, these are called as the oblate ones. Okay, now the given molecules, it is 14N, this is 7, and oxygen 8 and 70. So how can you tell what is gonna be the nuclear spin value for these molecules? So look for their atomic number and look for their mass numbers. Okay, if the atomic number it is even and the mass number is also even, the nuclear spin value in that case it is 0. Okay, if the atomic number it is even and the mass number it is odd, in that case the I value you have, which is n by the 2. Okay, and if the atomic number it is odd and the mass number it is even, in that case the I value it is in terms of the n, that is 1 2 3 like this. And if it is even atomic number and mass number is on n by 2, that means 1 by 2 3 by 2 5 by 2, the values you get in it. Now for the nitrogen, firstly you see atomic number it is odd and the mass number it is even, so it has the values which is odd and the even. So I value it will be n only, so its value has been found to be the 1, right? And for the oxygen, it is now atomic number is even and the mass number we get it as to be the odd in this, so n value it is gonna be half in this, right? Like this you get it, right? So if the A value it is 1 now, if it is 1, so the molecule is oblate. So that means nitrogen molecule it will be oblate, and the nitrogen, this oxygen molecule, half integral spin it is having, so it is gonna be your prolate, right? So oblate and the prolate. Here it is saying prolate and this is oblate. No, I can see in the option C it is oblate and the prolate. Option C will be the right one. From here the third answer will be the correct one. I hope this concept is clear. You should have just this idea that if I value it is greater than 0, it is oblate, and if it is 0 or the half, it is your prolate. And to how to depict the I values, so that is based upon their atomic number and mass number. Even and even it is 0, even and odd it is n by 2, odd and even it is n. Firstly is the atomic number, then is the mass number. Okay, so moving to the next one now. This question. A schematic rotational vibrational spectrum is depicted below, and four of the lines of this spectrum for a two diatomic molecules M1 and M2 are tabulated. So two of the molecules you are having, which is M1 and the M2. For this the spectra has been drawn, the lines has been given. So this M1, firstly these lines A, B, C, D they have given. So A value for the M1 molecule it is given us to be at 1540. Similarly the B value for the M1 has been given. Similarly the C for it and the D value. Same lines which is A, B, C, D for the M2 molecule they have also been given to us. Now next a condition is given if the reduced mass of the M1 is 3 times M1 reduced mass, it is 3 times that of the reduced mass of the M2 molecule. The ratios of their bond lengths are being asked to us. So that means R1 to that of the R2, this ratio is being asked to us. For the reduced mass, the relation is given to us. Okay, so now in this, the gap between the two of the levels, two of the lines that you have, this line, this gap it is gonna be 2b, right? Similarly between C and D also the gap will be of the 2b only. So for the molecule M1, firstly if you see 2b gap, it is gonna be 1564, which is the B value that you have, minus of the 1540, which is the A value that you have. So this difference, it comes out to be 24 centimeter inverse. That means B, which is for the M1 molecule, it comes out to be as 12 centimeter inverse of it, right? Similarly, for the M2 molecule also, the difference between these lines, we can find it. It is 1676 minus of the 1644. So this comes out to be as 2, and this is 32. That is equal to the 2B, which is for the M2 molecule now. So B for the M2, we get it as 16 centimeter inverse of it. So you are seeing for both of these levels, the rotational constants, we have found it out. The relation between the reduced mass is given. For the bond lengths, we have to find it out. B value, now I know it is H upon the 8 pi square into the IC. I value, it is mu r square. So B value, it will be H upon the 8 pi square into the mu r square into the C. So B value, we can see it is inversely proportional to the reduced mass and the square of the bond lengths, that is the r square of it, right? So now if I consider the rotational constant for the M1 to that of the M2, so it will be equal to reduced mass, which is of the M2, into the R2, R for the M2 square of it, upon the reduced mass, which is for the M1, R of the M1 and the square of it, right? This value, it will become now R1 by the R2. This value we have to find it out, right? This is for the first one. So this you can take it out on the other side, Rm1 upon the R of the M2, the square of it, it will be equal to reduced mass M2 into the B, which is of the M2, upon the reduced mass M1 into the B, which is of the M1. Now this relationships and the values we have found, just substitute that. Mu of the M1 is 3 times of the mu of the M2. So mu M2 upon the 3 times of the mu M2 into. Now B for the M2, it got it as 16, and the above value, which was for the M1, we got it as 12. Okay, so this and this, it is being cancelled out. So it is becoming 4 4s are 16, 4 3s are 12. So it is coming out to be 4 by the 9. So this is for the square, the ratio we are getting R for the M1 to that for the R for the M2. It is gonna be 4 by 9, the under root of it. So it becomes 2 by 3. So this is gonna be the ratio for their bond lengths. From the options, if you see now, 2 by 3, option first will be the right answer. Okay. Next, this question now, again December 2023, the transitions giving rise to the yellow sodium D lines are. So in the sodium, basically what happens, you have the various energy levels. The value of the energy level, it is inversely proportional to the L value, right? So for the different L values, you have for the S, P, D and the F terms, the L values is 0, 1, 2 and the 3. For the sodium lines, we have the energy levels, which is your S and the P levels you have. So now L value for the P, it is more, so that means it is gonna be of the lower energy, right? So here we have the P term and here you have this S term. Okay, and these terms, they are the 2P and the 2S. These are the levels, right? So now further, they show the splitting into the various energy levels. The S is not splitting, P it splits into the levels. Based upon the J levels, you have the lower J, because sodium atom now it is less than the half it, so the lower J value, it is gonna be of the lower energy. So it is gonna be 2P half, and here this you have 2P 3 by 2. Here you have 2S 1 by 2. Now when we obtain the sodium, this yellow lines you obtain, suppose the molecule you were having of the sodium atom, you were having it over here, it showed the excitation. So now after the absorption, the excited state, it is gonna be unstable, the molecule it comes back, and during that what happens, it shows the fluorescence, and during that the yellow lines, they are emitted. Okay, so basically the molecule is returning from the S half to the possibilities it is returning to the P3 by 2, and the next possibility it is returning to the 2P half. So the transitions which are occurring, it is for the 2s half to the 2P3 by 2, and the other is 2s half to the 2P half. So these are the transitions that occurs. So now from the options, 2s half to 2p3 by 2, 2s half to 2p half, option first one only is the right answer. Okay. Next you can see it is saying the D levels in rest 3 has been included. It is not present in the sodium, the spectra that you obtain. Okay. Next, this question. For a diatomic molecule with the n-harmonic oscillator mu e value, it is given as to be 536.2 centimeter inverse. So let's just note this, 536.2 centimeter inverse. The observed value of the fundamental frequency. The observed value of fundamental frequency, that means fundamental means 0 to the 1 transition it took place, to nu is equal to the 1. We got the gap which is mu e minus of the 2 nu e into the xe of it. Right now the magnitude of its third overtone is being asked to us. So you should know the value which is for the nth overtone. Nth overtone, we have the value which is n plus of the 1 into the nu e minus of the n plus of the 1 into the n plus of the 2 nu e into the xe of it. Now the third overtone they are asking, third overtone. So the value it's gonna be 3 plus 1, that is 4 nu e minus of, now 4 plus this will become 4 into the 5, that is 20 nu e into the xe of it. This value we have to find it out. So these values are given. For the fundamental band it is 529.4 centimeter inverse. So now nu e value you can substitute and find the value of nu e into the xe from this equation, and the nu e and the nu e into the xe value we will be substituting in this final equation that you want to find it out. Okay, so it will become the 536.2 minus of the 2 nu e into the xe. This is equal to 529.4, right? So 536.2 minus of the 529.4, this is equal to the 2 times the nu e into the xe of it. So this difference which is of the 536.2 minus of the 294 529.4, it will become 12 minus 4 which is my 8 plus, now here this 15 minus of the 9, that is 6. So 6.8 divided by the 2, this will be nu e into the xe. So nu e into the xe value we got it as 3.4 centimeter inverse of it. Now nu e you are having, nu e into the xe you are having, you are knowing the formula for the third overtone, just substitute in this. So the third overtone, that will be 4 nu e minus of the 20 nu e into the xe, 4 times the nu e value it was 536.2 minus of the 20 times the 3.4. Just solve this and get your answer from here. So 4 into 536.2, that becomes 2144.8 minus of 20 into 3.4, that becomes 68. So this both subtracting 2144.8. So it becomes 2076.8 centimeter inverse of it. This is gonna be the value of the third overtone. So 2076.8, first one option is given, that will be the right answer. Okay, now next, this question we are having, consider the two level system which is at thermal equilibrium. The ratios of the excited state population to the ground state are 0.50 and the 0.25 at 600 kelvins and at 200 kelvins. Energy gap between the two levels in the units of 10 to the power of minus of 21 joule is gonna be. Okay, so this you can find it using the Boltzmann distribution. Boltzmann, according to which you can find the population in the excited levels Ni upon the N0, it is Gi upon the G0 e raised to the power of minus of the del E upon the kBt of it, right? So now for the first excited state and for the ground state, so N1 by the N0, G1 and the G0 you will be having e raised to the power of minus of the delta E upon the kBt of it. This is what we will be having. Now what type of levels they have considered is it mentioned, so that we can get the values of the G1 and the G0. That is not mentioned, that which type of levels you are having. So what we can assume that the degeneracy is 1 only. This you can assume. Now at different temperatures these values are given. Just take that ratios. So firstly at 600 kelvins N1 by the N0, this is gonna be e raised to the power of minus of the del E upon the kb at the 600. So this ratio at 600 kelvins we have been given as 0.50, right? So this will be 0.50 e raised to the power of minus of del E upon the 600 into the kb of it. Or we can take ln of the 0.50, which is equal to minus of the del E upon the kb into the 600 of it, right? So let's just see what is the value of the ln of the 0.5, which is minus of the 0.693. This is equal to minus of the del E upon the kb into the 600, right? So this negative you can cancel on both the sides. So this is the first equation. Now at 300 Kelvin also the similar way we can see the ratio it is given, which is 0.25 will be equal to e raised to the power of minus of the del E upon the kb into the 300. So now ln of the 0.25, it will become, it is equal to minus of the del E upon the kb into the 300 of it. So ln of 0.25, which is minus of the 1.386, this is del E minus of the del E upon the kb into the 300 of it. Or this negative on both the sides again we can cancel. 1.386, it is del E upon the kb into the 300, right? So this now del E gap only we have to find it out. Okay, so what you can do is take the difference for both of this. So 1.386 minus of the 0.693, it will be delta E kb upon at the 300 minus of the del E upon the kb, which is at 600, right? So del E upon the kb into the, here it is, kb into the 1 by 300 minus of the 1 by the 600, right? So it will become, so we can take outside this values, we can take outside the 600. If I take it, so it will become 2 minus of the 1, right? So this value, it will be difference between these two, that is your 1.386 minus of the 0.693, which is equal to the 0.693 only. So 0.693 into the 600 into the kb value, which is 1.38 into 10 to the power of minus of 23. Okay, this is equal to the delta E on T, right? So here it was 2 minus of the 1 only. Okay, just solve this and get your answer. So now 0.693 into the 600 into 1.38, we are getting the value as 573.804 into 10 to the power of minus of 23. Now you see in the units of 10 to the power of minus of 21, I have to find this answer. So we can write it as 5.73804 into 10 to the power of minus of 21 joules of it, right? So value is 5.73. This is the answer that you are getting from the options. Now check 5.74 it is given. So this value will be the right one, right? 5.73, it was there, so close to 5.74 only. So this is the right one. I hope the concept is clear. Okay, now moving to the next question. This one you are having, it's from the June 2024 now. It says in the rotational Raman spectrum of a diatomic molecule, the energy gap between the first Stokes and the first anti-Stokes lines it is. Okay, so this is this type of the spectra that you obtain, the central relay line you can say, and on these lines, this side you have the Stokes shift, these are the Stokes, and on this side you have the anti-Stokes lines like this. The gap between the this level it is 6b, and this side also it is the 6b. Then you have the gap of the 4b on both these sides. Right, now the first Stokes line and the first anti-Stokes line, this gap is being asked to us. So total we can see 6b and 6b, so total it becomes the 12b. Right, so between the first Stokes and anti-Stokes, the gap is of 12b. Options third one will be the right answer. Okay. Next, this question now. The rotational quantum number associated with the most intense transition. Most intense transition will be taking place from the level which is most populated. Most populated level, that means the J max value they are talking about, right? Because rotational quantum number, so that means the J values. In the microwave spectrum of a diatomic molecule, it varies with the temperature, so J max value you need to find it out. So we know the general formula which is for the J max, it is equal to root of the kBT by the 2BHC minus of the half, right? So half we can ignore for the y. We are seeing that J max, it is proportional to the temperature which is in the power of the half. So J max is proportional to T under root of T in the under root you are having basically. So T raised to the power of half, option second one will be the right answer. Okay. Next, this question again, now it's December 2024. The atomic mass of the X and the Y are 5 atomic mass unit and 40 atomic mass unit respectively. So for the X, it is 5 AMU and it is 40 AMU. For the diatomic molecule, which is XY, the spacing between the two successive lines is of the 8 cm inverse in the microwave spectrum. So microwave means the rotational spectrum gap between the lines, it is of the 2b. So 2b it is given, which is 8 cm inverse. So from here B value we are getting it as 4 cm inverse of it, right? Next, the bond length is being asked to us. So that means the R value they are asking us to find out. So this is the bond which is X and Y. The distance between them is being asked to find it out, right? So now B value I know, it is H upon the 8 pi square into the IC of it. I value we know it is mu R square of it. So that means B value it is H upon the 8 pi square into the mu R square into the C. So this formula you can use now to find the value of the R over here. So B it is H upon the 8 pi square into the mu R square into the C. From here the R square, if I see, it is H upon the 8 pi square into the mu into the C of it into the B value, right? This is what we have. Now this value you see, H upon the 8 pi square into the C. This one, H upon the 8 pi square into this C. This value it is given to us. B value we have found it, and just the mu value additionally I need it over here. So firstly let's substitute this value. It is 2.8 into 10 to the power of minus of the 44 of it upon the B value that we have found it, which is 4 centimeter inverse. It is in the units of 4 centimeter inverse. So here you see, here the joule second square per meter inverse the units has been used. That means B value also I have to take it into the meters only, meter inverse only, I know that 1 meter it is 100 of the centimeters of it, right? So 1 centimeter it is 10 to the power of minus of the 2 meters of it. So that means 4 centimeter it will be 4 into 10 to the power of minus of 2 meters of it. So this value 4. Now 1 centimeter 10 to the power of minus of 2 meter, and then the inverse of it. So it will become 4 into 10 to the power of 2, right? Here the new value we have to substitute. So it will become 2.8 into 10 to the power of minus of 44 upon the 4 into 10 to the power of 2 meter inverse of it. Then the units it will become to be the same. Now the reduced mass value that you have to take it. Mu value it is m1 into the m2 upon the m1 plus of the m2. Here the m1 m2 you have the x and the y values, right? So now the x, the mass it is given 5 amu and the y it is 40. So it is 5 amu means 1.67 into 10 to the power of minus of 27 kgs of it into the y mass which was 40 into 1.67 into 10 to the power of minus of 27 upon the m1 plus m2, which will become 45 into 1.67 into 10 to the power of minus of 27. So one of this and this it will get cancelled out. So let's just solve what value we are getting for the mass in this. So it is 5 into 1.67 into 40, right, upon 45. So 7.422 into 10 to the power of minus of 27 kgs. So this is the mass that you are getting. Okay. So just substitute this in the previous value. You will be getting your answer, that is for the radius. Right. So here the mu value we can substitute now. R square it will be 2.44 2.8 into 10 to the power of minus of 44 upon the 400 into this reduced mass, which is 7.422 into 10 to the power of minus of 27 kgs of it. So just solve this and take this under root also, you will be getting. So 2.8 divided by 400, divide this with the 7.422. So it is becoming 0.000943 into 10 to the power of, now it is 44 minus of 44 plus of 27, that is becoming the 17, right? So now it's under root you have to take it. So this is the value of the r square that we are getting, right? So this one we can write it like this also. So here it is, firstly 10 to the power of minus of the 17, right? Or we can write it as 0.943 into 10 to the power of minus of 20. This will be in the meter square, the value we are having for the y. Now our value will be the root of this 0.943 into 10 to the power of minus of 20 of it, right? This in the meters you will be getting. So on solving this you get the value 0.9710 into 10 to the power of minus of 10 meters, or it is 0.971 angstroms of it, right? So this is the radius that you are this bond length that you are getting. Options you can check it. Now in the angstroms only it was being asked, so 0.97 I can see in the option second one it is given, so this becomes the right one. Okay, next this question now. The fundamental frequencies for the H2 H37Cl are this and this. So nu for the hydrogen is given, which is my 4395 centimeter inverse, and the nu for the H37Cl it is 2988 centimeter inverse of it. considering all the molecules are in their respective ground vibrational state. So this statement is important. We have to consider the ground vibrational state, the energy change in the reaction given below. Assuming the force constant, it remains the same with the isotopic substitution. So same type of the question it was being asked to us. Here also the reaction it was given, but in that case the frequency values they were given to us, right? So firstly you are talking about the ground state, right? So for the ground state vibrational level energy, it is half of the h nu of it. So now for the reaction change, the energy will be delta E. For this reaction, it is gonna be energy of the product minus of the energy of the reactant. This we have to divide it with the 2 because we are talking about the ground state energy. Now energy of the products, that will be the stretching frequency which is for the hydrogen plus of that of the deuterium which is with the 37 Cl, right? And similarly energy for the reactants, it is gonna be nu for the Hd plus of the nu which is for the H37Cl, right? So I'm having the stretching frequencies for the hydrogen and the HCl I'm having, but I'm not having it for the Hd and for the D37Cl. So these from the isotopic labeling we have to find it out. Okay, so let's do this. So firstly finding the stretching frequency which is for the Hd. So I know that mu value it is 1 by 2 pi c under root of k by mu. Mu is inversely proportional to the root of the reduced mass. This concept we are gonna use. This Hd upon the nu which is for the hydrogen, it will be under root of reduced mass which is of the hydrogen upon the reduced mass which is for the Hd. So this will be equal to under root of 1 into the 1 upon the 2, and here it will be 1 into the 2 upon the 1 plus of the 2, right? So it is becoming 1 by the 2, and in the numerator 3 we will be having, and this will be 2. So root of 3 by 4 times the stretching frequency of the H2 will give me the stretching frequency of the Hd, right? 3 by 4 times the stretching frequency of the H2, that we have 4395. 4395 centimeter inverse. So solve this and get your value. You will be getting it as 3806.18 centimeter inverse. So this is the stretching frequency for the Hd. Now for the D37Cl, D37Cl, so nu for DCl upon the nu for the HCl, it will be reduced mass for the HCl upon the reduced mass which is for the DCl. It is gonna be 1 into 37 upon the 38, which is the sum of both of this, upon 2 into 37, and here will be 39, right? So it is becoming root of 37 by the 38 into the 39 upon the 37 into the 2 of it, right? So this 37 and 37 it gets cancelled. So this multiplied with the stretching frequency of the HCl or the DCl we will be finding, it will be 39 upon the 38 into the 2 into the stretching frequency which was for the HCl, that is 2988 into the 2988, right? Solving this, the value you will be getting 2140.12 centimeter inverse of it. Now stretching frequency for all of these species we are having, so substitute this in the energy expression and get your energy reaction change, this change in the energies that you are having. So for the product it is H2 and the D, nu for the H2 plus the nu for the DCl minus of the nu for the D2 plus the nu for the HCl for the HCl. Divide whole of this with the half, you will be getting your answer. So now the values half. For the hydrogen we were having the value which is 4395. So it is 4395 plus of for the DCl, it is gonna be 2140.12 minus of mu for the D2 that you have got it. Sorry, not for the D2, this was the HD we were having. Sorry, it was the HD. For the HD we have found it 3806.18, 3806.18 plus of, now for the HCl the value it was 2988, 2988. So just solve this and get your value, which is gonna be minus of the 129.53 centimeter inverse of it. This is gonna be the energy change. Okay, so minus of 129.5 close to minus of the 130. Option B, it becomes the right answer. So in that question also, where the values were given to us, answer you were getting close enough to the 129 only, but there the values it was given here, they made it a bit lengthier one. Some of the values they gave it, the some values you have to find it out, then only you will be able to solve this. Okay, so next this question now, it's from the June 2025. The question it says, considering the potential energy to be at equilibrium position at Xa to be the 0, the internuclear potential, which is Vx, as a function of the distance x between two of the atoms in a diatomic molecule, is given as to be like this, where dE and the alpha are the two of the constants, the force constant of the bond between the two atoms that we have to tell them. Okay, so this potential which is given to us, it is basically the Morse potential. Morse potential. Now force constant you need to find it out. So I know that force value it is minus of the dV by the dx, right? Also we know that force value it is minus of the kx as per the Hooke's law. This is according to the Hooke's law, right? So in this case, you can equate both of this because both of this are the formulas for the force only. We can say that Kx is equal to the dV by the dx of it, right? Or we can say that K times the x, it is dV by the dx. We need the value of the force constant. So what you do is differentiate with respect to the x on both sides. On both sides, we will be getting k dx by the dx of it, and this will become d by the dx of the dv by the dx. So that means this side I am writing k value, it will be equal to d square v by the d of the x square of it. That means differentiating the value of the given potential energy with respect to the x two times will give me the value of the force constant in it, right? So now the v value we have been given, which is v as a function of x, it is given to us as dE into 1 minus of e raised to the power of minus of alpha x minus xe, and then the square of it, complete bracket, and then the square of it has been given. Now to simplify this, what you can do is let e raised to the power of minus of alpha x minus xe as to be the y over here, right? So v of the x, it will be reduced to dE into the 1 minus of y and the square of it. So now you differentiate it with respect to the x. So we will be getting dV by the dx, it will become dE 2 times the 1 minus of the y. Now minus of the, now for this dE is your constant, it has come outside. 1 minus of the y square it became, so n x raised to the power of the n. So n into the 1 minus of y it became. Now this bracket also you have to differentiate it. So with respect to the 1 it will be 0, and with respect to the y differentiation it will be minus of the dy by the dx. I hope it's clear. Okay, now this value of dy by the dx, this you need to find it out. So d by the dx of the y value that you assumed it e raised to the power of minus of alpha x minus of the xe of it, right? Now do its differentiation, e raised to the power of x, e raised to the power of x only, so x minus of the x it will be there. Now the power that you are having minus of the alpha into the x minus of xe, this too you do the differentiation with respect to x, we get minus of the alpha only. So dx by the x will be 1 only, and xc is your constant. With respect to that, it will be 0. So this is the value that you are getting, minus of the alpha e raised to the power of minus of alpha x minus of the xe, or it is minus of the alpha times the y value, right? So this substitution you can make in this. So we can give the numbering to the equations. This one first, you can say this, you can say it is the second one. This you have obtained it to be the third one. So put 3 in the 2, put 3 in the 2, we get dv by the dx, it will be equal to 2d into the 1 minus of y, 2 times de into the 1 minus of the y, dy by the dx. With the negative sign it was there, so it will become minus of the alpha times the y. So it is becoming 2 de into the alpha y into the 1 minus of the y. So this is after the first differentiation of the v with respect to the x that we are getting. Now again do the differentiation, again differentiate it with respect to the x only. So we will be getting d square v by the d of the x square. It will be 2 de into the alpha. It is your constant, so they are taken outside. Now first function as it is, that is y. Differentiation of the second, it will become minus of the dy by the dx plus of the second function as it is, differentiation of the first one. Right, now dy by the dx value you have found it, minus of the alpha times the y. This again you can substitute in this. Okay, so my d square v by the d of the x square 2 de into the alpha into the, now y into the minus of alpha times the y, which is dy by the dx, plus of the 1 minus of the y into the dy by the dx, which is your minus of the alpha times the y of it. This we are getting. So 2 de into the alpha into alpha times the y square plus of the 1 minus of the y into the alpha times the y. So negative sign it is there. So you can write this one as y minus of the 1. Y minus of the 1. So this is the value. Now alpha we can take it outside. So 2 de into the alpha square y square plus of the, now open this bracket, y square minus of the y it will become. This is what we are getting. So 2 times the y square minus of the y into the 2 de into the alpha square. Now the condition it was given that this is at equilibrium position. At equilibrium you have, at equilibrium xe is equal to the x only. So y that you assumed it e raised to the power of minus of alpha x minus of the xe, x minus of the xe. So here y will become e raised to the power of minus of alpha times the 0. So e raised to the power of 0, it will be 1. So y value we are getting as to be the 1. So that means this value it will become, that is d square by the d square v by the d of the x square. This is gonna be 2 de into the alpha square into the 2 times the 1 square minus of the 1. So 2 minus of the 1, that is 1 only. To 2 de into the alpha square, 2 minus of the 1, which is equal to 2 times the de into the alpha square of it. This is the value of the force constant that you are getting. Okay, so that means the k value it is 2 de into the alpha square of it. Okay, so options if you see now, 2 de into the alpha square, option second one will be the right answer. Okay, so I hope the concept is clear. Main thing it was just about the differentiation. You should have the idea how you can differentiate these type of the given equations. Okay, now the next, this question you are having, the rotational constant of a diatomic molecule is 2 cm inverse of it. That means B value is 2 cm inverse. the wavelength for the excitation of the laser. So lambda value is given, which is 333 nanometers of it, right? Now the frequency we know, wave number basically, that is units of the centimeter. It is 1 by the lambda of it. So for the incident radiation, you can find the wave number, that will be 1 upon 333 into 10 to the power of minus of the 9 meters of it, but we need it into the centimeters. So 1 meter is 100 of the centimeters, so it will become 10 to the power of minus of the 7 centimeters of it, right? So just solve this and get your incident frequency. Firstly, 1 upon the 333 into 10 to the power of 7, we are getting the value as 30030.03. So this is the incident wave number that you are having. Okay. Now next is assuming the model to be the rigid rotor model of a diatomic molecule. The first three Stokes lines they are asked in the centimeter for the rotational Raman. So this is the Rayleigh line, and here the Stokes lines you have it. The distance between them, the first it is at a distance of 6b, then we have the gap which is of the 4b gap, right? So from the incident one, the first Stokes line that you will be getting, first Stokes line, it will be nu, which is the incident, minus of the 6b. At this we will be getting 30030.03 minus of the 6 into the 2 of it, right? So 12 we have to subtract it from this one. So 30030.03 minus of the 12, it becomes 30018.03 centimeter inverse. So this is gonna be the first line that you are getting. So you can see 30018 in this option I'm having, and in this option. So from this second and fourth we can eliminate. Now in the similar way, the second Stokes line you can find it. Second Stokes line. So now you see this complete distance, it becomes of the 10b, right? Similarly for the second one, at the distance it will become of the 14b gap, right? So from the incident, subtract the 10b, so it will become 30030.03. This was only the value that you obtained, right? From this, subtract the value of the 20 centimeter inverse. So we will be getting 30010.03 centimeter inverse. So this value you see now, 30010, in this option it is given, here it is at 14. So this again, third one we can eliminate. So from first to only we can say that first is gonna be the right option. But let's find the third Stokes line also. Third Stokes line, which is at a distance of 14b now. So 30030.3 minus of the 14b of it. So minus of the 28 from here. 30030.3. Here the 03 it was there. So it will become 300 and the 02.03. This centimeter inverse. So this value you are getting 30002. So again you see 30002, option first only it is matching. Okay, so I hope it's clear. Next, so this was the last question that was from the topic, which is your physical spectra or the molecular spectroscopy. I hope all the questions that we have discussed of this unit, they are clear to you. So thank you so much for watching. I'll be meeting you in some new video now, where some new unit we will be starting. Okay, and make sure if you have understood the concept, then don't forget to like the video and do share it with your friends as well. And if you have not subscribed to the channel so far, make sure you subscribe to the channel also, so that you can get notification for the upcoming videos. Okay, so thank you so much. The question it says considering the potential energy to be at equilibrium position at xe to be the 0. The internuclear potential, which is Vx, as a function of the distance x between two of the atoms in a diatomic molecule is given as to be like this, where dE and the alpha are the two of the constants, the force constant of the bond between the two atoms that we have to tell them. Okay, so this potential which is given to us, it is basically the Morse potential. Morse potential. Now force constant, you need to find it out. So I know that force value, it is minus of the dV by the dx, right? Also we know that force value, it is minus of the kx as per the Hooke's law. This is according to the Hooke's law, right? So in this case, you can equate both of this because both of this are the formulas for the force only. We can say that kx is equal to the dv by the dx of it, right? Or we can say that k times the x, it is dv by the dx. We need the value of the force constant. So what you do is differentiate with respect to the x on both sides. On both sides, we will be getting k dx by the dx of it, and this will become d by the dx of the dv by the dx. So that means this side I am writing k value, it will be equal to d square v by the d of the x square of it. That means differentiating the value of the given potential energy with respect to the x two times will give me the value of the force constant in it, right? So now the v value we have been given, which is v as a function of x, it is given to us as dE into 1 minus of e raised to the power of minus of alpha x minus xe, and then the square of it, complete bracket, and then the square of it has been given. Now to simplify this, what you can do is let e raised to the power of minus of alpha x minus xe as to be the y over here, right? So v of the x, it will be reduced to dE into the 1 minus of y and the square of it. So now you differentiate it with respect to the x. So we will be getting dv by the dx, it will become dE 2 times the 1 minus of the y. Now minus of the, now for this dE is your constant, it has come outside. 1 minus of the y square it became, so n x raised to the power of the n. So n into the 1 minus of y it became. Now this bracket also you have to differentiate it. So with respect to the 1 it will be 0, and with respect to the y differentiation it will be minus of the dy by the dx. I hope it's clear. Okay, now this value of dy by the dx, this you need to find it out. So d by the dx of the y value that you assumed it, e raised to the power of minus of alpha x minus of the xe of it, right? Now do its differentiation, e raised to the power of x, e raised to the power of x only, so x minus of the x, it will be there. Now the power that you are having, minus of the alpha into the x minus of xe, this too you do the differentiation with respect to x, we get minus of the alpha only. So dx by the x will be 1 only, and xe is your constant, with respect to that it will be 0. So this is the value that you are getting, minus of the alpha e raised to the power of minus of alpha x minus of the xe, or it is minus of the alpha times the y value, right? So this substitution you can make in this. So we can give the numbering to the equations. This one first, you can say this, you can say it is the second one, this you have obtained it to be the third one. So put 3 in the 2, put 3 in the 2, we get dv by the dx, it will be equal to 2d into the 1 minus of y, 2 times dE into the 1 minus of the y, dy by the dx, with the negative sign it was there, so it will become minus of the alpha times dy, so it is becoming 2 dE into the alpha y into the 1 minus of the y. So this is after the first differentiation of the v with respect to the x that we are getting. Now again do the differentiation. Again differentiate it with respect to the x only. So we will be getting d square v by the d of the x square. It will be 2 dE into the alpha. It is your constant, so they are taken outside. Now first function as it is, that is y. Differentiation of the second, it will become minus of the dy by the dx plus of the second function as it is, differentiation of the first one. Right, now dy by the dx value you have found it, minus of the alpha times the y. This again you can substitute in this. Okay, so my d square v by the d of the x square 2 dE into the alpha into the, now y into the minus of alpha times the y, which is dy by the dx, plus of the 1 minus of the y into the dy by the dx, which is your minus of the alpha times the y of it. This we are getting. So 2 dE into the alpha into alpha times the y square plus of the 1 minus of the y into the alpha times the y. So negative sign it is there. So you can write this one as y minus of the 1. Y minus of the 1. So this is the value. Now alpha we can take it outside. So 2 dE into the alpha square y square plus of the, now open this bracket, y square minus of the y it will become. This is what we are getting. So 2 times the y square minus of the y into the 2 dE into the alpha square. Now the condition it was given that this is at equilibrium position. At equilibrium you have, at equilibrium xe is equal to the x only. So why that you assumed it e raised to the power of minus of alpha x minus of the xe, x minus of the xe. So here y will become e raised to the power of minus of alpha times the 0. So e raised to the power of 0, it will be 1. So y value we are getting as to be the 1. So that means this value it will become, that is d square by the d square v by the d of the x square. This is gonna be 2 dE into the alpha square into the 2 times the 1 square minus of the 1. So 2 minus of the 1, that is 1 only. To 2 dE into the alpha square, 2 minus of the 1, which is equal to 2 times the dE into the alpha square of it. This is the value of the force constant that you are getting. Okay, so that means the k value it is 2 dE into the alpha square of it. Okay, so options if you see now, 2 dE into the alpha square, option second one will be the right answer. Okay, so I hope the concept is clear. Main thing it was just about the differentiation. You should have the idea how you can differentiate these type of the given equations. Okay, now the next this question you are having, the rotational constant of a diatomic molecule is 2 cm inverse of it. That means B value is 2 cm inverse. The wavelength for the excitation of the laser. So lambda value is given, which is 333 nanometers of it. Right. Now the frequency we know, wave number basically, that is units of the centimeter. It is 1 by the lambda of it. So for the incident radiation you can find the wave number, that will be 1 upon 33 333 into 10 to the power of minus of the 9 meters of it, but we need it into the centimeters. So 1 meter is 100 of the centimeters, so it will become 10 to the power of minus of the 7 centimeters of it. Right, so just solve this and get your incident frequency. Firstly 1 upon the 333 into 10 to the power of 7, we are getting the value as 30030.03. So this is the incident wave number that you are having. Okay, now next is assuming the model to be the rigid rotor model of a diatomic molecule. The first 3 Stokes lines First three Stokes lines they are asked in the centimeter for the rotational Raman. So this is the Rayleigh line, and here the Stokes lines you have it, the distance between them. The first it is at a distance of 6b, then we have the gap which is of the 4b gap, right? So from the incident one, the first Stokes line that you will be getting, first Stokes line, it will be nu, which is the incident, minus of the 6b. At this we will be getting 30030.03 minus of the 6 into the 2 of it, right? So 12 we have to subtract it from this one. So 30030.03 minus of the 12, it becomes 30018.03 centimeter inverse. So this is gonna be the first line that you are getting. So you can see 30018 in this option I'm having, and in this option. So from this second and fourth we can eliminate. Now in the similar way, the second Stokes line you can find it, second Stokes line. So now you see this complete distance, it becomes of the 10b, right? Similarly for the second one, at the distance it will become of the 14b gap, right? So from the incident, subtract the 10b, so it will become 30030.03. This was only the value that you obtained, right? From this, subtract the value of the 20 centimeter inverse. So we will be getting 30010.03 centimeter inverse. So this value you see now, 30010, in this option it is given, here it is at 14. So this again, third one we can eliminate. So from first two only we can say that first is gonna be the right option. But let's find the third Stokes line also. Third Stokes line, which is at a distance of 14b now. So 300.3 minus of the 14b of it. So minus of the 28 from here. 300.3, here the 03 it was there. So it will become 300 and the 02.03. This centimeter inverse. So this value you are getting 30002. So again you see 30002, option first only it is matching. Okay, so I hope it's clear. Next, so this was the last question that was from the topic, which is your physical spectra or the molecular spectroscopy. I hope all the questions that we have discussed of this unit, they are clear to you. So thank you so much for watching. I'll be meeting you in some new video now, where some new unit we will be starting. Okay, and make sure if you have understood the concept, then don't forget to like the video and do share it with your friends as well. And if you have not subscribed to the channel so far, make sure you subscribe to the channel also, so that you can get notification for the upcoming videos. Okay, so thank you so much.